just a little bit of background to myself. I previously worked for a company for many years, 34 years actually, and then I was approached by Danfoss to say would like to come and work for them, and basically tried to understand why I should do that. And what I found was that Danfoss had been generating a new marine drive specifically built for this type of operation, and the ESG, which to be fair I'd hardly really heard of, was well installed in the company. So 2.5 years on now, it's been a great move for me, and we are now heavily involved in all the electrification of vessels, from both the smallest vessel, crew transfer vessels, right the way up to manoeuvring capabilities on large container vessels. So I mentioned Steve Moore, fortunately can't be here today. He's part of the UK team, is both a solution sales manager and also a highly dedicated engineer, and is involved, like myself, along with all marine projects, along with our Centre of Excellence team within Danfoss to integrate various levels of electrification, be it pure electric, hybrids, serial hybrids, or parallel hybrids. I'd like to just run through some of those during the presentation. So our founder was Mads Clausen, and he had the expression that if others can do it, so can we, and if they can't, we'll do our best to still do that, and we have a chance. And that was the foundation, 1933, that allowed us to start innovating and following through with that actual statement. And within the first 10 years, he developed a full thermostatic control system, which then is used throughout industry and in domestic applications now. But where are we now? We've moved into the more global mega trends that we have to follow to actually incorporate our products to get efficiency up and get better control of the environment. So we obviously do address climate change, of which we have a total division looking after that, which looks at heating and ventilation and efficient use of air movement. We've got urbanisation, more and more people coming into a central location from more rural areas. We've got electrification. Electrification is the core of our business, be it on land, on sea, or any other application that requires battery energy storage to be coupled with electric motors. Digitalization is another massive sector which also encompasses data, and again for all vessel and all development, data is important to us, so we have to have data centers. Data centers also need cooling efficiency, and this also extends through to vessels. It's the same principle. So, as an overall picture, buses, trucks, any type of cargo movement, we can use the same technology, and that allows us to get that investment of money from those sectors and bring them into the maritime sector as well. So the automotive, for instance, is well proven in battery energy storage, battery transfer, shore charging systems. What we've got now is we've got to integrate those into vessels. And how do we do that? We have a number of different platforms, but one of the platforms, what we call the Editron system, we can scale this knowledge and equipment to whatever level we wish. That could be super yachts. We've already mentioned container ships. That's more for manoeuvring rather than actually long distance. Let's not get carried away. We're not going to be using battery energy storage to do transatlantic runs. But what we are going to be using is we're going to be using for inshore manoeuvring, especially in the harbours and ports as the regulations tighten up. And also, we're going to use them for operation when it's stood at the shore, so we're not running diesel generators whilst up at the shore. Crew transfer vessels, I'll come on to those specifically, but crew transfer vessels is absolutely perfect for environmental change. If we're within 20 nautical miles of the shore, it's a perfect distance to be travelling in order to allow recharging to take place, both onshore and when you're offshore. And I say offshore because we're in collaboration with a company whereby we have the perfect green solution. And that is we go out to site to a wind turbine application. We then drop an umbilical down from the wind turbine and charge the vessel whilst we're working on that wind turbine. At the moment, it's proved at 250 kilowatts, and we'll be deploying one next year, which is about 2 megawatts. So we'll be using the MCS system for charging, and that gives us a total 100% battery-operated crew transfer vessel. So we offer the full package. We have the motors and also the inverters. I'll come on to the more technical things. I'll try and keep it relatively straightforward. If anybody wants more information about how we do this technically, please feel free afterwards. I'll go into as much depth as you wish. So if we do a quick comparison, why do we go electric? Mainly because of the efficiency of it. Traditional marine diesel motor, diesel engine, 30%, maybe 40 to 50 if it's running its peak revs, and a very, very efficient one. Compare that to your motor capabilities for efficiencies, and we're up at 96%. So we've got a massive differential here of how to transfer power efficiently. The units themselves are very compact, and this particular system is based on what we call a distributed technology. So rather than having one central point where all the weight is, we can distribute these inverters throughout the vessel, near the motors, and then just take the power leads, to all intents and purposes, the DC power, to a local inverter, and then actually feed the motor from there. The unit itself is a universal piece of kit, electronic piece of kit. For those of you who are sad enough to look into this sort of stuff, then we have active front end, microgrid, inverter control. All of those things are done by the same module. So, for instance, to generate our hotel supply, we need both 400 volts, we need 215, 240, whatever it is. We can generate that. We can do that from a battery system, we can invert it, and we can generate both neutral-based single-phase supplies or full three-phase supplies at 415, 440, whichever is required. On the propulsion machinery, very important, we need to get compact, high density, high power into a very small space. And the only way you can realistically do that is to use permanent magnets, and also we can use synchronous reluctance to assist those permanent magnets. And by using that particular technology, we can generate full torque across the range of its speeds. The comparison in size of these units, you can see, which hopefully is the same as my screen, considerably smaller. So that again, as everybody knows, especially marine architects, there's no room on a vessel. You're the last person to get that little bit of a corner to fit your equipment in. So this is really critical to design. So if we look at it on a diagrammatical format, then we've got the sort of things you'd expect to see on a vessel. You've got bow thrusters, you've got winches, you've got mid thrusters, stern thrusters, you've got your main propulsion sectors, and then it may be a special cable laying vessel. So you could also have draft haulback systems to hold back cable that's been deployed into the sea. You may have cable drum engines that are paying out a 7,000-ton carousel of cable that's been subsea laid. And these, once we start on these projects, these are live, these actually happen. We're deploying subsea cables across the Atlantic, and it is an amazing procedure to be able to see something working and delivering that cable subsea. What we then need to do is control all the systems. And it sounds quite easy, yeah, we'll just put a computer on there, it'll be fine. No, what we've got a great bunch of acronyms coming up. So we've got a battery management system, a BMS. We've got an ECS, which is our Edutron control system, our own system. And then we've got another system above that, which is the PMS, which is the power management system. And that'll typically be something like Vard, for instance, who's a large shipyard. They'll have their own power management right at the top of the hierarchy, and they'll be the ones who are sharing the power to do the propulsion, get the balance in. It'll come down to us as a command. We'll then use our own balancing with our own inverters to get that power distributed correctly. And then we have the batteries. The battery guys, they don't trust us, they don't trust anybody. And if you want the warranty on a battery, you have to use their battery management system. So that's always part of their scope. And that's not just us, any competitor, it's always the same. They have to provide their own battery management system. But they're all working on a same comms level, which is CAN bus in this case, same as the automotive industry. So you can see again where we're drawing that knowledge from other sectors. And what that allows us to do is get cross-sectional communication from all those three platforms on one common network. So effectively, it's just like plugging in on Ethernet to all intents and purposes and getting that cross-level communication. The way that we structure the words, the way we structure the status words, the command words to everything, that's all even more technology, but essentially it's a method of having a common structure that flows throughout whatever vessel size it is. All of these components then come back up to a central communication point, which are multiple HMIs, which give the operator at the very top level what's happening, what's the state of the battery charge, are we taking energy, are we pushing energy back in them, how much do we want to use the batteries, how much do we want to mix that with standard propulsion. All those factors are commanded right at the top. And what we do in any vessel is we tend to distribute everything in DC. So we generate in AC, we make a common DC bus, and then we redistribute that energy through the system. The reason for that is the most efficient way to transmit energy is through a DC bus bar system. So if we run through a few case studies, there are a number of vessels that we've worked on. The Ørsted, for instance, we've done a number of vessels for Ørsted. If anybody was at Seaworks, then they would have seen one on the pontoon there, which was one of our vessels, and that had 8 of the Volvo D8 internal combustion engines driving our own generators, which then fed serial hybrid. So serial hybrid is where we take a generator, then we just literally have some cables going to the motor at the back of the vessel, or the inverter at the back of the vessel to drive it. So you haven't got any mechanical coupling between the two. This particular one, you can see there's a split between the electrical propulsion and diesel propulsion. So that was a slightly different vessel to what was actually at Seaworks. They're getting more and more advanced, and they're heading more and more, certainly from a crew transfer vessel point of view, to pure electric. Because the batteries are getting better, the technology is getting better, and we've really got a grip on that sort of side of things. And this is just a quick overview to give you an idea of what's going on, because it's kind of not traditional, really. So we've got in this case, the Volvo Penta engine there driving the EMPMI, which is a permanent magnet motor. So that's the heart of the generation. That's our power station. So from there, we'll then take that into these left-hand units here. We'll make that into a common DC bus that we talked about, and then we'll distribute that throughout the whole vessel. And then we'll take that off, put it through inverters, put it through microgrids to make the hotel load, all that sort of thing. We can just bolt on at any point throughout the vessel. It gives you an idea of the layout. It's a totally different technology. We haven't got gearboxes and all the mechanical stuff we normally have. It's all just done through power electronics. The power electronics itself is all water-cooled. Water-cooled gives us a really high power density, so we can get the units much, much smaller. So a typical unit like the one up there on the left, that will be a 300 kilowatt unit, so very small power density within these modules. That's an example of what's happening further downstream. So this is when it actually ends up at the propulsion motor rather than a generator now. And these two units up at the top left are the inverters that convert from the DC back into the AC for the motor. So if we dig a little bit deeper into what's happening on the electronic side of things, so everyone hopefully stays with me a little bit. So you can see the middle thick bar, which is the DC link. So we've got 3 generators up in the top left. internal combustion engines, if you like, the diesels, they're driving the generators. The generators go through those square boxes that basically, to all intents and purposes, rectifies, makes it into DC. Then we distribute that throughout the vessel. And then hanging off that DC, you can see on the left-hand side, we've got one of the propulsion motors on the right-hand side. So we always split the system, port and starboard, because we need redundancy. We need it for certification, and we also need it just to be sensible, so we don't take the whole system down if we lose one side. In between that, we've got isolation in the middle, where we can separate the two sectors. So if you have a problem, we can just open those breakers. On the right-hand side, we've got the battery bank. So the battery bank has another clever bit of electronics that goes from the DC. But you can't just connect the DC. This bus is running up at about 750 volts. We can't just connect that to a battery. We need to control the voltage to that battery. It's a charge system. So that's another one of those little aluminium boxes that deals with that sector of it. Great example, especially today. So we've got the Uber boat. So there are now 3 of those vessels on the Thames, which are all operating under this Danfoss Editron system I've just been discussing. So there are twin motors in there, and it's all the same architecture. It's got the same DC bus, it's got the distribution, everything based on that criteria. So on the Uber Clippers, this is now what we call a parallel hybrid. Okay, so a parallel hybrid, I'm sure you all know, but for those who don't, parallel hybrid is typical, where we've got an internal combustion engine that feeds into a gearbox, and then we also have a feed from a motor which goes into that same gearbox and then down to the propulsion propeller. From there you can do PTO or PTI, so we can take power out or we can put power in. If we're putting power in, we're helping that main drive with the motor, and if we're taking power out, then we're actually using the internal combustion engine to drive the generator to charge the batteries up at the top right-hand side. So this is where, when I talk about all the bus systems, there is a lot of complexity going on to balance all these systems and get them all to communicate. And that's part of our design, our project, is to make sure that all these systems work, communicate, and they do it safely. This is another vessel. A lot of these are very similar now. This particular one, it's also a parallel hybrid system, but it just shows different operations. It's a unit which again is in daily operation. These aren't sort of sketches on a drawing. These are actually up and running. So the full electric, this is an example of the CTV, where we're actually solid with batteries on there. We have no other propulsion method, but we have the split of the port and the starboard, and we have this ability to break off either side in order to keep isolation in case one side goes down. And we also have the ability to share batteries from one side to the other, so we can get that share between the port and starboard from any of the battery systems. And also we have the ability to take the charge which comes from the shore. We can take that in through one side, take it across to port or starboard, or we can charge them all if we have a big enough source on the shore supply from that one common DC bus. Okay, so we have an option of bringing in AC from the shore, or we can bring in DC from the shore. So in certain cases where we hear about shore power supplies, then they tend to be based on a shore power supply that takes AC, it has a converter on the shore, makes it DC, and then we plug into the vessel with DC. And that way we can get much higher charge currents, and we use what we call the MCS system. So we're into megawatt charging systems then. Okay, so I hope that's given you a reasonable overview of what's happening within our type of products. It's very difficult to run a session like this when I need to understand who knows at what level. What I would say is, if anybody wants to know anything in depth about how we actually do that communication, what's involved technically, and how we get there, then I'm absolutely more than welcome to go into more detail on that. But generally speaking, we've done these presentations for the last 5-10 years, And what we're finding now, 5, 10 years ago, head in the sand, it's not going to happen, don't want to know. What we found a few years ago was, this is going to happen, we better start thinking about it. And what we're finding now, literally, I would say this year, growing exponentially, is not only are people thinking about it, we have orders, we have delivered equipment, and we have equipment that's already in production. We have one yard in particular, which is full with 3 vessels under construction now, which are all hybrids or pure electrics. So I hope that gives you an insight from the electronic side of things, and it's a general overview of what we're up to, but there's a lot more involved if anyone wants to know. Thank you.